Okay, welcome back. All right, before I begin, any questions, comments, concerns? We're on chapter 12, slide 4, where we're introducing the concept of a mole, okay? And that is the common unit that we're going to need to use when we talk about grams of compound X reacting with grams of compound B to give us grams of product, whatever it may be. And in order to talk about weight, we can't go weight to weight relationship. We have to convert into a common value or unit, which is a mole. And mole is simply nothing more than a number, okay? Just like a dozen. A dozen, we got a number, it means there's 12. Okay, it just so happens that the mole happens to be a very large number. And to give you an idea of how big that is, if you had a mole of softballs, then altogether all those softballs would be the size of the earth. So it's pretty hefty. But atoms are extremely tiny. And it's to me, it's really mind-boggling when we think about a mole in the size of the atom, or not the size of the atom, but the size of the atom in respect to all around us. So when we talk about a mole of water, you'll be surprised with, the number is 6.02 times 10 to the 23rd molecules of water. And that represents what, 16, 17, 18 grams. More on that in a second. That's just 18 grams of water. So imagine all the water on Earth, how many molecules of water are out there? The number is just astronomical. All right, so on the periodic table, and I think I started to mention this, was, give me 1 second, my periodic table is not up. The units of the periodic table for their respective atomic weight. Remember, the atomic weights were the numbers underneath the symbol. And so for carbon, we have here the atomic weight, not the mass number, not the whole number, but the atomic weight was the sum of a weighted average of all of the isotopes for that particular atom. So for carbon, we ended up with a weighted average of atomic weight of 12.01, okay? And that means that, well, it doesn't mean anything yet, but the units for atomic weight are grams per mole, okay? Grams per mole. So therefore, if you weigh out 12.01 grams of carbon, you have exactly 1 mole, okay? If you weigh out 19 grams of fluorine atom, or just a single atom of fluorine, it will have 1 mole, okay? Now, thing to remember here, going back to the physical states of the elements, remember we have 7 diatomic elements. So be careful when the question says, if you have 1 mole of oxygen gas versus 1 mole of oxygen atoms. If they're saying atoms, we're talking about in one single atom. If they're talking about oxygen gas, fluorine gas, hydrogen gas, then we're talking about the diatomic species, and therefore you got to double the atomic weight for that, okay? And so as the case here, as the elements get larger in size, obviously they got more protons, more neutrons, more electrons, they get bigger in size, therefore their weight gets bigger. So even though we have 1 mole is 6.02 times 10 to the 23rd individual atoms, their particular weights would be greater. So xenon, 1 mole of xenon would weigh 131.29 grams. 1 mole of krypton would weigh 83.80 grams, okay? So on and so forth till we get, down here to helium. 1 mole of helium would weigh 4 grams, okay? 4 grams. So just like um, uh, eggs is a good analogy that I use quite a bit, that if I say, for example, I'm going to run through some examples with respect to eggs. So you might think, well, I thought we're talking chemistry here. But the point of this exercise is to get you to extrapolate what we talk here about into the concept of the mole, because we know the concept. We got that pretty, I mean, all of us know about a dozen. And so if, for example, we're talking about small eggs, okay, and for argument's sake, let's just say that they weigh 100 grams per dozen, okay? Medium, we're just going to simply double. Obviously, they don't weigh that much, but we're arbitrarily throwing some numbers in. So 200 grams per dozen, okay? And then large, let's just continue with the trend of 300 grams per dozen, okay? And in all these cases, obviously, when we say 100 grams per dozen, we're talking about 12 small eggs. For median eggs, we're talking about 12, right? All of them, 12. That's their common factor. There's a dozen, okay? And so I could, if necessary, for example, if someone said to you, all right, how many dozen would you have if you had 50 grams of small eggs? Okay. If you had 50 grams of small eggs, how many dozen would you have? What do you guys think? We're just talking about the small ones. You might take a shot at that? 50 grams of small eggs, given that the small eggs for a dozen weighs 100 grams. What would you say you had? You had half a dozen, exactly, right? Because we know a dozen weighs 100 grams, so 50 would be half a dozen, which would mean how many eggs would that be? Obviously, it would be 6, right? And we can go through the same exercise if we had 100 grams of medium eggs, well, again, also half a dozen there, which again also meant 6, etc. So if we have 150 grams, okay, we will have how many dozen? Now, you got the grasp of the dozen, but let me take it one step further here, okay? And we're just going to stick with the small ones, okay? And we understand all of that. All right. And we had that factor here of 100 grams per dozen. Okay. That is our ratio. As any ratio, I can write it one or two ways. Just like when we did the conversion factors, 100 grams small eggs per 1 dozen. Okay. Or I could say 1 dozen small eggs per 100 grams small eggs. Okay. Now, which ratio we use depends on the question. So earlier I said, all right, if you have 50 grams of small eggs, how many dozen does that correspond to? And yes, we got an answer very quickly, but we set that problem up like we did before with respect to the conversion factors. Okay, and we emphasize that stepwise process. Why? Because I mentioned at that time that we're going to set these up to do calculations for chemical calculations, and we're going to use the same technique. So we're looking for dozen with respect to units. So obviously, dozen goes on top, and grams go in the denominator, right? Because we want grams to cancel out. We want the units of a dozen to remain. That's our conversion factor right here. We want 100 in the bottom and the denominator, right? And so that represents with 0.5 dozen is our answer. If I have 50 grams of small eggs, which then when you talk about an individual number, well, how many actual A's does that correspond to? Well, I know you can do that very quickly, but you would set up the same scenario with respect to a conversion factor, because we know that there are 12 per dozen, right? There's Avogadro's number here, but we got 12 units, in this case, 12 eggs per dozen. All right. Now, did I set this up correctly? Okay. And so 0.5 times 12 is 6 eggs. Okay, my dozens cancel out. Now I could have set this up all in two units. Okay. So I use the analogy of the eggs to get you to start thinking again how we did the conversion factors, because we're going to use that same technique when it comes to calculations. Okay. And so right now we're talking about the conversion factors, the atomic weights of the elements. And if we take carbon, it's 12.01 grams per 1 mole. Those are their units, right? So I can write it either like that, or I can write it with 1 mole of carbon is equal to 12.01 grams of carbon. Okay. And so if I'm asked the question, if I have 10 moles of carbon, well, what does that correspond to with respect to grams of carbon? Okay. All right, so we set the problem, what we're given, what we're looking for with respect to the units, what we know about carbon with respect to the atomic weight. So we have a conversion factor here. We want moles in the denominator because we want moles to cancel, and we want grams in the numerator because that's the units we're looking for. Okay, and so if I have 10 moles of carbon, I'm going to multiply it by 12.01. Okay, so roughly 120 grams of carbon represent 10 moles. And that is given moles, we want to get to grams, but you can reverse the process and say given grams, we want to go to moles. Okay, so let's do one real quick. And here we're talking about something about carbon. And recall the density calculations. We have grams over milliliters, and we can use milliliters and so forth. We were given grams, we want to go to volume. We're given volume, we wanted to go to grams. Same setup here, similar type of calculation. So in this case, let's say we're given 100 grams of carbon, and we need to know how many moles does that represent, moles of carbon. Okay, so this is our given. We know we're going to need a conversion factor here. I'm going to need grams in the denominator because I want grams to cancel. And I want moles in the numerator because those are the units I'm looking for. Okay. And so there's 1 mole per 12.01 grams. And so I set the problem up properly. Now it's up to you to run the calculation and figure out how many moles 100 grams of carbon represents. Okay. So that is eventually what we're going to be doing with respect to these type of calculations. So on the periodic table, you should be able to go to the periodic table, and if the question is asked, well, if I have 12.01 grams of carbon, how many moles does that represent? Obviously 1 mole. Same thing for sodium. Sodium weighs 22.99 grams per mole. So 1 mole is equal to 22.99 grams. Okay. And don't forget that if you're dealing with the diatomics, you double that atomic weight, okay? So if you're dealing with oxygen, oxygen has an atomic weight of 16, but it's O2, then double that up. That's 32 grams per mole. Right, as explained, moles is simply nothing but a number, in this case 6.02 times 10 to the 23rd units, entities, whatever you're counting. It could be atoms, ions, molecules, formula units, etc. It's anything, bananas, oranges, etc., whatever you are counting. All right. Now, we talked about the molar mass. That carbon, you simply just go to the periodic table, and from what is called the molar mass, which is slash atomic weight. Okay, we use that term interchangeably. Okay, because later down the road, we're going to be looking at the molecules, and we're going to calculate their molar mass. Okay. And that's related to how many atoms of each we have in that molecule. We just add up their atomic weights. So carbon, gold, and sodium, their molar mass is given on a periodic table, 12.01, 196.97, 22.99 grams per mole, respectively. Okay. All of these, if you're weighing out that amount, 12.01, etc., you have exactly 1 mole of those elements, which means you have 6.02 times 10 to the 23rd atoms. Just like we did earlier with the small eggs, we said, all right, we have a dozen, half a dozen of small eggs for that particular weight we calculated. Then we go one more conversion factor that tells us that half a dozen represents 6 eggs. That's what we're doing here. We will be doing here. All right, so, but let's first learn to calculate the molar mass, because yes, all the reactions we've been putting together, okay, we got those 6 reactions that we just went over. We learned how to balance them, okay? So the next step now is to learn how to calculate the molar mass, and it's a straightforward thing. Basically, you take the element or the compound, and you add up the number of atoms of each atom that's in that compound, multiplied by its respective atomic weight, and sum everything up, and that is the molar mass. Okay, but before we do any of that, we have to figure out what the formula is, and that's why we've been writing formulas out, given the names. Okay, and we're given barium hydroxide. So the first thing we got to do is what? Write them into ions. We know that barium has a +2 charge, right? Because it's a element, it belongs in group 2A, 2 valence electrons. It's a metal, it's going to lose electrons. Therefore, you have a +2. This is an anionic compound. So we got to put everything into ions before we put them together to figure out the formula. The hydroxide is the polyatomic ion that you go to the periodic table, and you'll find that its formula is OH negative, right? So we need two hydroxides for every barium. So the formula is Ba parentheses OH 2, and that is our formula. So we need the formula to accurately calculate the molar mass. Okay, so now determine how many of each atoms do we have. We got 1 barium in the formula, we have 2 oxygens, and we have 2 hydrogens. Okay, given the atomic weights for each one, multiplied by how many of each atom we have, we end up with the total molar mass, and we end up with something like this. And there's the formula, okay? And so here we have barium hydroxide. Its atomic mass is 137.33, which brings me to the point. When you use atomic weights, okay, or molar mass of the atoms, use our periodic table with our numbers, okay? Because Canvas is geared to answer the correct, to present the calculations, let me restate that. The calculations are based on the atomic weights of the periodic table we offer. You can go to Google and you'll get a variety of atomic weights with a lot of numbers after the decimal point, which if you use those can cause you to have a number that's off maybe by 10 2/10. And then Google, then not Google, but Canvas checks it as incorrect, okay? So to prevent any of those problems, use the atomic weights of our periodic table. If Google, I don't know why I got Google in the brain, but Canvas counts it wrong and you know it's correct, as always, I go back and check it, and if you are correct, I definitely have no problem giving you credit for it. It could be a little burp in Canvas, not giving you the correct points for that, okay? So barium has its atomic weight, atomic mass at 137.33 grams per mole. There are two oxygens, as we stated. Each one weighs 16, okay? So that's going to be 32 grams per mole. And then there are two oxygens. Each one weighs, its atomic mass is 101.0, 1.01 times 2 gives you 2.02. And if we tally all that up, we end up with the molar mass for barium hydroxide of 171.35 grams per mole, okay? And here we have this ratio again, which, by the way, now you can write it in one or two ratios with the grams in the numerator, moles in the bottom. Okay, this is for barium hydroxide. Or invert it, 1 mole over 171.35. Okay, so you got two ratios here, and which one you use, like we've been doing already, it depends on the question being asked and what you're trying to calculate. Okay, but before you can get to that point, you have to be able to, from the name, determine the formula correctly, be it an ionic compound or even being a covalent compound, okay? Then from the formula, determine the number of atoms number of different atoms in that compound, multiply it by the atomic weight times whatever number of atoms you have for that particular atom, and then sum them all up, and that becomes the molar mass for that particular compound, okay? And don't forget the units. Units are grams per mole. For some reason, sometimes students tend to forget the mole part, and they write down grams, but it's not, that's incorrect, okay? This is a sum of atomic weights, which is in the units of grams per mole. Okay, now going back to Avogadro's number. Avogadro's, again, also a ratio, okay? It is 6.0. You can write it one or two ways, written on top of here. Either what we got to the left or to the right. And keep it in mind, it's a number, just a count. So it's units. I just used the term units, but like I said, it could be atoms, molecules, bananas, oranges, whatever you are counting. So you can write it with 6.02 times 10 to the 23rd per mole, like shown on the left, or invert it, okay? And then use it the same way we've been doing the calculations, depending on the units that we're looking for, depending on the units that we are given, that determines which manner you're going to set up that ratio so you can get that thing to, so you can get the units to cancel out. All right, so here we have a problem that says how many calcium atoms, okay, are in a quarter of a mole, 0.250 moles, okay? So you can see that 0.25 is a quarter of a mole, all right? So your number should be approximately a quarter of 6.02 times 10 to the 23rd, to give you an idea. And that means that remember, I've always stated with respect to your calculations, look at your answer. Does the answer make sense given the mathematical function you did? Okay, and so here you're starting off with less of a mole, okay, and with less of a mole, that number that you're going to end up at the end should be less than Avogadro's number. Okay. Anyway, let's set that up. So we have what we're given, 0.250 moles of calcium. Okay. And we need to know how many atoms of calcium are involved here. And so I set up my conversion factor. I got moles that I'm given, so moles will be in the denominator and then atoms will be in the numerator, okay? So that means that I'm going to be using Avogadro's number as written on the left. So we got 6.02 times 10 to the 23rd divided by 1 mole, okay? And we go through that, we set that up, and you end up with 1.51 times 10 to the 23rd calcium atoms. Even if you are, hold on 1 second. Okay. Even though you're dealing with a fairly small number, 0.25 mole, it's roughly a quarter of a mole, you end up with an extremely large number of atoms, 1.51 times 10 to the 23rd. It still adds a lot of atoms in that small amount of moles. Now, keep in mind, hopefully you're thinking ahead. Since we're dealing with moles, we're given 0.25 moles, and then given that the molar mass is units of grams per mole, guess what? We can eventually get to grams because, the concept of the mole sometimes can be a little bit difficult. Plus the fact that you're in the lab and you're weighing things out. You don't weigh things out in moles, you weigh things out in grams. So we're eventually going to convert the grams into moles. All right. So the next one here. It says, well, how many moles? Second. How many moles are in 3.75 times 10 to the 27 molecules of oxygen gas? All right, so 3.75 times 10 to the 27 molecules, I'm doing shorthanded MOLEC molecules of O2, okay? And we're looking for how many moles that represents. All right, so that means we got our molecules in the denominator and moles in the numerator. And so we're using that, we put an Avogadro's number in the denominator. And we're 1 mole, okay? Now here, we're not looking for atomic weights. We know that oxygen is diatomic. We don't have to double the 6 Avogadro's number because we're working in moles, okay? So moles, calculate the moles for this number of molecules of either oxygen gas or oxygen atoms in this scenario is going to be the same, okay? You only need to know it's diatomic when we start really doing calculations and getting into grams. All right, so we set that up and we have, imagine that, we have 3.75 times 10 to the 27 molecules. It's a little bit over a mole, all right, of molecules of oxygen. That corresponds to over 6,000 moles of oxygen. Specifically, 6,230. Okay. Keep it in mind, don't forget the sig figs. Given the problems go by the sig figs that you're given in the problems, because Avogadro's number, how can you state this? You know, right now, you may not think this, we're dealing with whole numbers. You know, Avogadro's number is a whole number, no different than the number one. It just happens to be, 6.02 times 10 to the 23rd. That number has, 602, 6 trillion. All right, that's a whole number. And so we're not really dealing with whole numbers here. Okay, with this number, with this example, because we have a whole number here and a whole number here, and which results in an infinite number of sig figs. So my suggestion is just go off of what you were given, like 3.75, and then convert your answer with that number of sig figs. When you are given a number like 0.25 moles, you got moles, those are actually measurements. You're going to see that. And so the 0.25 would actually be a factor in determining sig figs. But Avogadro's number is not. Avogadro's number is simply a whole number. It's like 12. One dozen equals 12. And that is an exact number and therefore wouldn't play a factor in sig figs. Okay. All right. All right, in this example, we are going to do some more calculations. We're going to convert from grams to moles. Okay. Earlier I stated before, right now we've been working with molecules using Avogadro's number, going from molecules to moles, moles to molecules. Okay, so we're going to take it one step further now, where we're going to now be able to convert from grams to moles, because again, in the real world, we weigh things out in grams. We're not dealing directly with moles. We have to know the moles involved in the reaction, but we don't have a balance that goes out there and weighs moles. You weigh it in grams. All right, so we're going to use the molar mass, either in the ratio of grams over moles or moles over grams, and which one we use depends on the question, right? So you're going to read the question carefully. So here's an example of being aware of the question, because if you notice there, it says how many grams is 1.667 moles of oxygen gas. Okay, we have the gas. So now we need the molar mass of oxygen gas. Okay, and oxygen itself, the atom of oxygen is 16, but oxygen gas is diatomic, so we need to double that. So the molar mass of oxygen gas would be 32.00 grams per mole. Okay, and that is the molar mass of oxygen, the NMR. Okay. All right, let's set up the problem now. How many grams? So we're looking for units of grams. And what we're given is 1.667 moles. Okay, so moles comes originally from a measurement. And so that number would be used to determine the sig figs. And we're looking for grams of O2. Okay. All right, so we need moles in the denominator and grams of oxygen in the numerator. And so we have 32.00 grams of O2 divided by 1 mole. Moles cancel, leaving me with grams of oxygen. Okay. All right, so let me clear it up a little bit, and here we go. Okay, so we set that up. Notice my units of moles canceling. Okay, leaving me with units of grams. So 1.667 times 32 gives me 53.34 grams of oxygen, represent 1. 667 moles of oxygen. And that number sounds like it's a reasonable number, right? Because you know that 1 mole of oxygen, 1 mole will weigh 32 grams. And we're starting off with a little bit greater, about 1.5 times more than 1 mole. So your number that you get of 53.34 is reasonable. Now, what can, and I do that because you can see here, if you inadvertently reversed it and put 32 in the denominator, you're going to have a small number, which is inconsistent with the mathematics that you're doing, right? So that is just a check to make sure, okay, that number seems reasonable, given what I did mathematically. Okay, here they're asking you how many moles are in 45 grams of silver. So, well, silver is an atom, so we can look up silver, and it is 107, it's a mass, atomic weight, 107, what is that? Double check. 0.87 grams per mole. Okay. We want to know how many moles we have if we start off with 45 grams. So write down what we given, 45 grams of silver. Okay, we're going to have a conversion factor here. We're looking for moles of silver. Okay. We're given grams, so I'm going to have grams in the denominator, and that will be 107.87, and 1 mole of silver in the numerator. Okay, my grams cancel. When I do the math, now I just plug those numbers in, and you should get the following. Okay, 0.45. 0.42 moles of silver represent 45 grams of silver. All right. So here's an example of your given grams. Okay. And you need to convert to moles. Now, why would you do that? Because maybe you need to react silver with something else, and you have to determine how many moles of something else you need to run that reaction. Okay, now that I'm in silver, then I rely on the balance chemical equation of that reaction, which gives me that new ratio that allows me to go into moles of something else. Okay, and once I'm in moles of something else, based on the molar mass, I can get to grams of something else. And our middle unit, our common factor here is moles. All right, here we go. How many grams is 0.0554 moles of water? Okay, so obviously we need to figure out the formula for water. We all know that is H2O, okay? From that, we need the molar mass. And so we got 16 grams from oxygen. We got 2 hydrogens. Each one is 1.01. So we get 2.02 for the hydrogens and for the oxygen. So the molar mass for water is 18.02 grams per mole. Okay. 18.02 grams per mole. Question says here, how many grams is 0.055 moles of water? So let's write down what we're given. I know it does sound redundant, but I am going through a systematic approach to the problem, setting it up properly. Eventually, you don't, depending on yourself, you may not have to go through all the steps I'm doing. All right, so how many grams? So that's what I'm looking for, units, grams of H2O, okay? So now I have something that I need moles in the denominator, grams in the numerator, grams of H2O, moles of H2O, which is the molar mass. So it's 18.02 in the numerator and 1 in the denominator. Moles cancel, leaving me with units of grams. So I take 0.0554, multiply that by 18, okay? And that would tell me how many grams that small quantity is worth. Okay, so 0.0554 moles of water weighs 0.998 grams of water. Okay, very small quantity, almost 1 gram of water has in it 0.0554 moles of water. And then we can multiply that by Avogadro's number, and it'll tell you how many molecules we actually have of water. So, but think about this for a second. Let's take the molar mass of water, okay, which is 18.02 grams per mole. All right, so if you go and weigh out 18.02 grams of water, you have 1 mole, okay? You have 6.02 times 10 to the 23rd molecules of H2O, which is a big, big, big number. All right, that's just 18 grams. Now imagine all of the water here on Earth, okay? Some astronomical number. And then figure out how many molecules of water that corresponds to, and you're going to be, I don't know. I know I was impressed with that number. It is humongous. Yeah, just think of just the water in your body, all right, and how much water there is, and that tells you how many. You can calculate how many actual molecules you have of that in your body. It's just humongous, humongous. All right. All right, so here we have a couple of things that we need to look at the problem, okay? All right, we're looking at potassium, so we want to figure out the atomic mass of potassium. For potassium, it is 39.10 grams per mole, okay? We're talking about the atoms. We're looking for atoms here, so guess what? We're going to be using Avogadro's number. So 6.02 times 10 to the 23rd atoms per 1 mole. So that factor would be involved there, right? I think we got everything we need. We're starting with atoms. Okay, so we got atoms, and we need to get to grams of potassium. Okay, well, we cannot go going directly from atoms to grams. We have to go through moles, then to grams. Okay, see how the moles is the common unit that gets us from point A to point B with respect to these type of calculations. So atoms to grams, grams to atoms require us to go through moles. All right. So let's set this problem up. We are given 4.75 times 10 to the 16 atoms of potassium. Obviously, we need a conversion factor here, which is good old Avogadro's number. We got atoms, we got to convert to moles right here. Okay, so we're bringing Avogadro's number. Bear with me for a second here. Right, and so we use 6.02 times 10 to the 23rd atoms in the denominator, 1 mole in the numerator. Atoms cancel out. Okay, so at this point in the calculation, if we stop it right here, then that would take the 4.75 times 10 to the 16 atoms and get me into moles. Okay, But the question asked us for grams. And I forgot to put grams over here, so I won't lose sight of where I'm trying to get to. So I need one more conversion factor here, which would get me into grams. I need moles in the denominator and grams in the numerator. My moles cancel, okay? So that will be 39.1 in the numerator and 1 mole, excuse me, numerator and 1 in the denominator, okay? Notice all the units canceling out. Atoms cancel out, moles cancel out, leaving me with units of grams. And I set up 2 conversion factors. A typical type of calculation that we're going to be doing requires at least at the minimum 3 conversion factors. Okay. The key point is this right here. This is what I just explained. I cannot go from atoms to potassium to grams directly. Okay. I have to go through moles. Right? Moles is my common factor. We set that up. I end up with, imagine, look at that large number that you have, 4.75 times 10 to the 16 atoms of potassium. That is a humongous number. Move that decimal point over 16 times. It gives you an idea how big that number is. And when you go through that mathematical calculations, that number of atoms represent only not 3.96 times 10 to the negative 6 grams. That's a tiny number, okay? Most balances that we have in the lab cannot measure that. So you got 1, 2, 3, 4, 5, and 6. Let me make sure I got this right. 1, 2, 3, 4, 5, and 6. Look at that number. Written down longhand, extremely tiny. At the most balances that can weigh out analytical balances in the lab that we have generally are in thousands place, right? That one would be difficult to measure. Not unmeasurable, it's not impossible to measure, but not with the majority of tools that we have out there. But having said that, the point is this: look at that small number, how small it is as far as grams. Okay. And even that small number tells you that the actual atoms are extremely large, 4.75 times 10 to the 16 atoms. Extremely large number. Okay. So these are examples of converting from grams to moles. And a couple, one here that at the end was to go from grams to atoms to moles. Okay. Now, which brings us to gases. Okay, gases. We had talked about the volume of gases and the physical properties, where we said that gases like liquids, their volume was dependent on their container. And in fact, they really have no set volume. However, it depends on the conditions, okay? And these conditions are called STP, standard temperature and pressure. Okay, so we are looking at 0 degrees Celsius and at 1 atmosphere. Okay, 0 degrees Celsius, which is cold, and at 1 atmosphere of pressure. We're approximately 1 atmosphere down here in Arizona. Obviously, if you went up to a high mountain like Colorado, the number there would be much less. All right, so at those temperatures, we have an interesting phenomenon. And this is as follows. 1 mole, and this only pertains, I can't overemphasize this only pertains to gases, okay? And obviously only when you are at 0 degrees and you're 1 atmosphere, STP. So if we look at hydrogen gas, fluorine gas, ammonia gas, xenon gas, and methane, all of them have in common, we have 1 mole of those gases, right? Which means that they have Avogadro's number of those gases. They're each going to have a different molar mass. Okay, hydrogen is going to have, two hydrogens, each one at 1.1. So its molar mass is 2.02 grams per mole. Fluorine is also diatomic, so that would be 38.00 grams per mole. Ammonia, that's the one nitrogen and three hydrogens, gives us a molar mass of 17.04 grams per mole. Xenon gas has a molar mass of 131.29 grams. And finally, methane here, carbon, add up the carbon for oxygens, we end up with 16.05 grams per mole. So all of these molecules or compounds we've given, they're all different molar masses, obviously, are different weights, right? But they all have in common 1 mole, and they all have in common the same number of molecules. Now, at STP, what they also have in common is that they occupy 22.4 liters per mole. Okay, and so here now, if you have a gas and you put it and you have 1 mole of that gas and the temperature is 0 degrees Celsius, okay, and it has 1 atmosphere, it now has a known volume of 22.4 liters, okay, for all these gases. That 22.4 liters per mole, guess what, is another ratio, just like the molar mass atomic weight. So we can use that as liters per mole or moles per liter, depending on the question being asked to calculate. All right, so let us clear this up. So here, this is basically what I just stated. But I can't overemphasize the conditions where this is true. And that is 0 degrees Celsius and 1 atmosphere. If the problem doesn't state that you are either at STP or they actually state the temperature in the atmosphere, if they don't say that information, then you can't do the calculation of use that ratio of 22.4 liters per mole, written in that form, or 1 mole per 22.4 liters. And like any ratio that we've been working with, which one you use depends on the question, okay? All right. So let's let's work through one of them. Okay, so what is the volume of 1.25 moles of argon gas at STP? All right, and so you see that our relationship is 22.4 liters, okay? Plus, you're being told 1.25 moles. It's over 1 mole, it says 1.25 mole. So the volume should be greater than the 22.4. Okay, so it's 22.4 plus a quarter more. Okay, based on the problem that you're given here. So, as any question, we've been doing so to date, we write down what we're given. We have 1.25 moles of argon, okay, and we need to get to volume of argon. That's what we're looking for. So since we are at STP, we can use that relationship where we have moles in the, we need moles in the denominator and liters up on top. So 22.4 over 1 liters, okay? Got my units, I'm set up properly to give me the proper units. So 28.0 liters of gas, okay, for 1.25 moles of argon gas. Okay, Next question. How many moles is 30.002 of O2 gas, of oxygen at STP? Okay, so how many moles if we're given 30.4 liters of O2? Okay, I'm going to need a conversion factor, and I need to get the moles of O2. Okay, notice what we're given. We're given 30.4 liters. All right. Well, we know that 22.1 mole is 22.4 liters, and so we're given 30.4. So our number should be a little bit greater than 1, right? Okay. So we set it up like we keeping track of my units, liters in the denominator, moles in the numerator. So you got 22.4, 1 moles. Okay. And that is 1.36 moles of O2, which is consistent with the volume that you're given of 30.4 liters. So you can notice a little trend here, which also can help you when we're talking about atomic weights. We want to go from grams to moles. Okay, if we're given moles, we're multiplying by the liters per mole to give us liters. If we're given liters, we are dividing by the liters to give us moles. All right, then the next one, excuse me. Now, here, we're at STP still. We want to know what is the molar mass of 4.5 liters of gas. Okay. And so this scenario is, we started just the units. We want to go to liters to grams mass, right? But we can't do it directly. We have to go through moles to get there. And also to get back. If we're given grams, you can go to liters, but we can't go directly unless we go through moles. All right, so we want to know what is the mass of chlorine gas. Chlorine is diatomic. Okay, so you get a double that atomic weight. And so setting that up, clear this up here. You should end up with the following. Okay. All right, so look at my units. First unit gets me out of liters and into moles of chlorine gas. Okay. Now, then the molar mass of chlorine, which is, being Cl2, it's double the 35.45, and its molar mass is 70.90 because chlorine gas is diatomic. And we set up with grams in the numerator, moles cancel. So now we end up with units of grams, which is what the question asked for. Okay. So like I stated, we can't go directly from liters to grams. Can't do that. We have to go through moles. Okay, we have to go through moles. And the other takeaway is that we have these conversion factors, these ratios that go from grams of what we're given to moles of what we're given, and then these conversion factors we use these ratios now get us to moles of what we're looking for. And from the moles what we're looking for, we can get now to grams of what we're looking for. Okay, but all got to go through moles. okay? And that's what this thing is all, this flow chart is all about right here. There will be another flow chart down the road that adds another dynamic, another part to the whole picture. But here's the thing, as I explained, I can't go through any direction without going through moles. And so if I start off with grams, I need the molar mass, which is in grams per mole, okay? Which then puts me into moles of whatever I'm given. Okay, now at this point, I can go one or two directions. If I'm being asked to figure out how many atoms or units or whatever, then I use Avogadro's number here to get me to that point. Or if I'm at STP, okay, at STP, then I can actually calculate the volume. And so my suggestion is to, when you do your calculations, to keep this flow chart, readily available, because you can see how you need to get from point A to point B. Okay. Let's do a for instance. All right, let's just say you're given X grams of some material, and you're wanting to determine the volume for that number X grams. So you're going in this direction. All right, so I got X grams and I need the molar mass. So grams, I wanted to demonstrate here just the units. I'm not putting any numbers in there. Okay, so I got the first, which is the molar mass. I need moles over grams. That cancels out, right? And I'm trying to get the volume. And so I use the liter over moles. Moles cancel, leaving me units of liters, okay? Which is I'm striving for. Now, I can go the opposite direction. It's not a one-way arrow here. I could be given volume and I need to calculate grams. Furthermore, I could be given volume and I need to calculate maybe the number of atoms or molecules that I'm working with. And so these arrows, are two directional. I can go from grams to molecules or atoms or formula units or what have you. Okay. Or I can go to the yellow part in both directions. Okay. Regardless of which part you're at, I can only do it when I am working, converting everything to moles. So keep that in mind. Moles is my common factor that connects me from point A to point B. All right, so here we have a couple examples. Is how many grams does 17.35 liters of neon gas mass at STP? Okay, so we write down what we're given. Unfortunately, I also wrote down what the answer is, but that's okay. And there's the answer. So we write down what we're given, which is 17.35 liters, okay? And we're trying to calculate the number of grams. So our first factor, given that we at STP, our first factor converts those liters into moles of neon gas, okay? So here I'm at moles, change this. At this point, I'm in moles of neon gas, okay? But I'm looking for grams. So I need the molar mass to get me to grams. So the molar mass of neon is 20.18 grams per mole. My moles cancel, as my liters did. And now I have units of grams, and now it's a matter of you typing in the numbers. So 17.35 liters of neon gas corresponds to 15.6 grams. Now, with respect to sig figs, okay, you have 4 sig figs at 17.35, but our answer is 15.6. I stated that we don't use the atomic masses for sig fig determination, okay? Those are not used. So that implies that there's 3. That implies that this unit here is a factor in our sig figs, and that is correct, because the 22.4 liters is a measure, liters per mole. And so it could be a factor with respect to sig fig if you utilize it in the calculations. Okay. And that's why you have 3 sig figs as an answer. All right. The next question was, how many atoms does this correspond to? Well, here we go. We set up like we did before. Again, I need a conversion factor where at STP, I need to convert that 17.35 grams, 17.35 liters to moles. The difference is the next factor is I use Avogadro's number, okay? And that itself, Avogadro's number will then tell us how many atoms we are dealing with. And so here's the cool thing. If you are at STP and you have 17.35 liters of argon gas, that represents 15.6 grams of neon gas, and that represents 4.66 times 10 to the 23rd atoms of neon gas, okay? You know, relatively small volume, a humongous number of molecules, humongous to the 23rd, just a little bit less than a mole, okay? All right, let's do a couple more here. I think we got 1 or 2 more. No, we don't, sorry about that. Okay, we're gonna deal with density here in a bit. So the takeaway from all these calculations we did here was the concept of the mole. The concept of the mole is our intermediate when we want to get from grams of component reactant A to reactant B. Okay, if I want to get from grams of A to grams of B, I got to go through moles. So I got to take the grams of A and convert it to moles, okay, based on the molar mass of A. And then depending if it's a reaction process, use that ratio to convert it to moles of B. And then from the atomic weight of B, eventually give me 2 grams of B, okay? All right, which brings us to density. Density, we did talk about that before, where it's simply a ratio of mass over volume, okay? But we can actually calculate the density of gases at STP, which is simply the molar mass divided by the molar volume. And so if we want to know the density of ammonia at STP, we need the molar mass, which means we got to get the molar mass for ammonia, 1 nitrogen, 3 hydrogens. And then we know the molar volume is 22 liters per mole, okay? And so when we do that, its density at STP is 0.767 grams per liter. If we look at the units here, when we do this mathematically, on the top side, we got grams per mole. Okay, and the numerator. And then in the denominator, we got liters per mole. So, you know, we're taking a fraction, dividing by a fraction. Where we do the units, we invert. So we got grams per mole. And we're going to multiply that by moles per liters, so you can see the moles cancel, leaving us with units of grams per liter, okay? But we can only do this for a gas that is at STP. All right. And so, which brings us to another aspect about the percent composition. We talked about actually figuring out the molar mass for a compound. Okay, we simply added up all the atoms and that gave us the molar mass. Now, with that bit of information, we can take one step further and calculate the percent composition. Okay, so if we take, in this example, let's say it is water here, we got H2O. We're looking for the percent composition of hydrogen and oxygen. Well, the way we do that is the first thing we calculate the molar mass for this. We did this earlier, and this is 18.02 grams per mole. One oxygen, two hydrogens. Okay, so that is the molar mass for H2O, which needed us to also, we know the contribution for the hydrogen, which is 2.02 grams per mole. So taking the contribution for just the hydrogen, all of the hydrogens, dividing it by the molar mass, multiplying by 100, gives us the percentage of hydrogen. We do the same for oxygen. Okay, oxygen, there's only one oxygen at 16. Total molar mass is 18, multiplied by 100. The percent composition for oxygen is 88.79. Now, what should happen after you do all that for all the atoms, they should tally up, the percent should tally up to be 100%. Now, this is true for any molecule of water, given wherever it's formed, here on Earth or out in space. If it has that structure of H2O, it would be the percent composition of 11.2% hydrogen and 88.79%. In the actual lab, we would do this quite a lot. Every time we made a new compound, synthesized a new compound, we clean it up. We had an idea of what the structure was based on some other instrumentation, and then calculate the percent composition, send it up for analysis to verify it. Then it would come back, and if we were correct, our numbers would be right, also correct. So an additional bit of information for the compounds we made. So with that, we're going to do this example here, and we're going to call it a day. Find the percent composition for TNT. Anybody know what TNT is? Dynamite. TNT is dynamite. It stands for trinitro-toluene. And there's the given formula for toluene. Let me give you a side question about this. Anybody know who discovered TNT? Very famous scientist. He has a prize named after him. Exactly, Noble. Noble and his people were created this stuff, and very dangerous, and obviously a dangerous chemical to make in the lab. Very sensitive. Anyway, its formula is given as follows. There are 6 carbons, 5 hydrogens, total of 3 nitrogens, and 6 oxygens. Okay. So with that, always use the atomic weights from the periodic table. Okay, carbon has 12.01. There's 7 of them. So it's a total contribution for carbon of 84.07 grams per mole. Hydrogen, there are 5 hydrogens, each one bringing in 1.01. So it's a total of 5.05 grams per mole for the hydrogens. The nitrogen, there are 3 of them, each at 14.01, total of 42.03 grams per mole. And then there are 6 hydrogens, each one bringing in 16 for its molar mass, for a total of 96 for oxygen. So we have a grand total of, or a molar mass of 227.15 grams per mole. Okay. And so 200, if you weigh out 227.15 grams of TNT very carefully, you have exactly 1 mole, or 6.02 times 10 to the 23rd atoms or molecules of TNT. All right, now given that information, now we take each individual atom and its contribution and divide it by the molar mass times 100, and we end up with 37.01% carbon. Hydrogen brings in at 22.2% hydrogen. Nitrogen is at 18.50 for nitrogen, and oxygen it contributes 42.26%. For a grand total, that should be a grand total of 100 there, plus or minus a tenth or so, but yeah. All right, so I tell you what, we're going to call it the end here, but try these at home, okay? And then if I'm giving you the answer, but I'm not showing you how to calculate it. But see if you can try these at home. See if you come up with the answer. So, for example, first one. How many liters would 3.425 grams of carbon dioxide occupy at STP? Okay. So you have the grams of carbon dioxide. You want to get to liters of carbon dioxide at STP. Remember, I can't go directly, so I got to go through the units of moles. Number 2 says, how many molecules are in the same quantity of carbon dioxide? 3.425 grams of carbon dioxide. Calculate how many molecules that has, and you should come up with 4.68 times 10 to the 22 molecules. And then if you had 3.0 times 10 to the 15 molecules of carbon dioxide, what would its mass be? You should come up with 2.2 times 10 to the negative 7 grams. All right. So yeah, so try these at home and see how they work. Other than that, congratulations. We are done with chapter 12. And yeah, so if you have any questions concerning these calculations, come Tuesday, bring them in and we can go over the problems. And